Hi, this video will be about how to survive the global pandemic with homemade hand sanitizers. We're going to look at how to survive this COVID-19 crisis in simple terms and how hand sanitizers work. Then we're going to look at how to make an at-home hand sanitizer. So part 1, surviving the COVID-19 crisis. How? First, stay at home. Second, wear your mask. Third is to wash your hands and use hand sanitizers. These 3 things are the most simple things you could do to prevent getting COVID-19. Everyone says it's important to wash our hands, but what happens on the microscopic level that keeps us from getting sick? That leads us to part 2. How does hand sanitizers and soaps kill viruses? The COVID-19 virus, also known as SARS-CoV-2, consists of many parts. First, there's the spike glycoprotein. Second, there's the envelope protein. Membrane protein is another factor that consists of this virus. The RNA and the nucleoprotein that is inside of the virus is enclosed by a lipid bilayer membrane. So what happens when the virus is exposed to soap? A soap particle consists of a hydrophilic head and a hydrophobic tail. This compound is also known as being amphiphilic because it has both properties of liking water and not liking water. This is same as a phospholipid molecule, which consists of a hydrophilic head and a hydrophobic tail. This allows the soap particle to insert itself in between the phospholipid molecules. When the soap molecules meet with the phospholipid molecules, they form a compound called micelles. Micelles are spherical compounds that consist of soap molecules and phospholipid molecules. These molecules form due to the attraction that the hydrocarbon tails of a soap molecule and a phospholipid molecule feels. As mentioned, the hydrophobic tails of soap and phospholipids attracts one another because of the London dispersion force between the hydrocarbons. On the other hand, the hydrophilic heads form the outer layer of the sphere that protects water from entering to the hydrocarbon tails. This eventually destroys the phospholipid bilayer that is enclosing the materials, also known as cytoplasm of the virus. Now we're going to take a look at the chemical structures of ethanol and phospholipid. Ethanol is a main component of hand sanitizer. Ethanol has a short hydrocarbon chain on the left side, and it has a OH region which is available for hydrogen bonding. Now let's take a look at phospholipids' chemical structure. As mentioned before, phospholipids are consisting of a hydrophilic head and a hydrophobic tail. So when ethanol gets near a phospholipid, the OH region of ethanol starts forming hydrogen bonds with the hydrophilic head of the phospholipid. This creates room in between the phospholipids, eventually leading the membrane to be loose, increasing the membrane fluidity. Now let's take a look at how hand sanitizer kills the virus visually. Ethanol, being a very small polar molecule, allows ethanol to move through the phospholipid bilayer. As we can know from the chemical structure of ethanol, it is also amphiphilic, which allows ethanol to mix in with the phospholipids. The ethanol eventually reaches the cytoplasm through osmosis. As we saw in the chemical structures, when ethanol meets phospholipid, it is going to increase the membrane fluidity, allowing the ethanol to enter more. Also, the spike glycoprotein of SARS-CoV-2 will denature. The shape of the protein is held together by hydrogen bonding in the tertiary structure. Ethanol interferes with these hydrogen bonds that consist the shape of the protein by forming hydrogen bonds with the parts that were supposed to be connected to one another. Now, part 3, at-home hand sanitizer production. Here is how you can actually make a hand sanitizer that would work according to the WHO guidelines.
So to make our hand sanitizer, we're going to follow the WHO guidelines, which suggests final concentration of the hand sanitizer solution to be 75% bivolume isopropyl alcohol, 1.45% bivolume glycerol, and 0.125% bivolume hydrogen peroxide. However, in my case, we're starting with 91% alcohol, 99.5% glycerol, and 3% hydrogen peroxide. So to get from our starting solutions to a 500 milliliter preparation of a solution following the WHO guidelines, we're going to be calculating how much of each reagent to use using the equation M1V1 equals M2V2. So here we're doing a 500 milliliter preparation of hand sanitizer, so the final volume will always be 500 milliliters. M2 is the concentration of our final product, so we're just going to plug in the WHO guidelines into M2, and then we're going to be solving for V1 with M1 being our starting concentrations. So, for example, to calculate the volume of alcohol required, we're going to plug in the numbers. So, 0.91 times V1 equals 0.75 times 500. So to get V1, we'll just solve 0.75 times 500 milliliters over 0.91, and this should equal 412, but there's only two significant figures, so say 410 milliliters. And you'll just repeat that for all of the reagents. So here, I've already measured out the desired volumes of water, alcohol, glycerol, and hydrogen peroxide, and we're just going to mix them into one single container. When mixing, be sure to wear gloves and goggles, as alcohol and hydrogen peroxide are both strong eye and skin irritants. Here, I'll pour in the alcohol first. Then the hydrogen peroxide. Then the glycerol. And I'm going to try and use the water to rinse out the remaining glycerol. As you can see, glycerol is quite viscous. Alright, then we're just going to cover the container, gently shake to mix, and there you have it, homemade hand sanitizer.